Welcome to Chapter 3, Section 3. Real and complex number system. In this section, we will study the set of rational numbers and important extensions of the integer number systems. In our previous session, we learned that integers allow us to solve problems involving positive numbers, negative numbers, and zero. However, there are still many questions that cannot be solved using integer alone. For example, consider the question 2x plus 5 is equal to 6. Solving for x gives x 1 over 2. While 1/2 is a valid number, it is not an integer. Similarly, many real-life situations involve sharing, measuring, and comparing quantities that are not whole numbers. To represent such values, mathematicians develop the set of rational numbers. A rational number is any number that can be written in the form of a over b, where a and b are whole numbers and the b is different from 0. The set of rational number is denoted by the capital Q. Examples of rational numbers include 1/2, -3/4, 5, an even number, and the zeros. Because each of them can be expressed as a fraction of the two integers. Rational numbers extend the integer systems and fill the gaps between integers. For example, between 1 and 2, there are infinitely many rational numbers such as 1.1, 1.25, 1.5, and 1.75, and so on. This makes the rational number system much richer and more flexible. Next, let us examine the operations on the rational numbers. Rational numbers are closed under addition, subtractions, and multiplications. This means that whenever we add, subtract, or multiply two rational numbers, the result is always another rational number. In addition, rational numbers are also closed under division, provided that we do not divide it by 0. Just like integers, rational numbers satisfy several important properties. Addition and the multiplications are commutative, meaning the order of the number does not affect the result. They are also associative, meaning the grouping of a number does not change the result. Furthermore, multiplication is distributive over addition. Rational numbers also have identity element. 0 is the additive identity because adding 0 leaves a rational number unchanged. 1 is a multiplicative identity because multiplying by 1 does not change the value of the rational number. Another important property is the existence of inverse. Every rational number has an additive inverse, which produces 0 when adding to the original number. For example, the additive inverse of 3/4 is -3/4. Every non-zero rational number also has a multiplicative inverse or reciprocal. For example, the multiplicative inverse of the 3/4 is 4/3 because their product equal ones. We can also compare rational numbers using order relations such as greater than, less than, and equal to. These relations follow the same logical rules that we studied for natural numbers and integers. An important feature of rational numbers is their decimal representation. Every rational number can be written in the form of either a terminative decimal or a repeating decimal. For example, 7/5 equal 1.4, which is the terminating decimal, while 2/3 equal 0.6666, which is a repeating decimal. We can also convert decimals back into fractions. Terminating decimal can be written as a fraction by placing the decimal numbers over a power of 10 and simplifying. Repeating decimals can also be converted into fractions using algebraic methods. In this session, we have explored the set of rational numbers, their operations, properties, inverse, order relations, and decimal representations. Rational numbers allow us to represent fractions and perform calculations that are impossible within the integer systems alone. In the next session, we will study irrational numbers and discover why some numbers cannot be written as a fraction, leading us toward the complete set of real numbers. See you in the next session.